All right, welcome back to the deep dive. Today we're diving into multi-fidelity policy gradient algorithms. And
sounds pretty dense, right?
yeah, a little bit, but I think it's going to be a good one. And it's super relevant for anyone working with like robotics or any sort of complex simulation where you're trying to get an AI to, learn something that needs a ton of data. So, the classic problem is you've got this high fidelity data that's like the gold standard, right?
Yeah.
The really accurate real world stuff, but it's expensive or difficult to collect. Think training a self-driving car. You can't just have it racking up millions of miles on real roads, right? Too risky, too slow.
Exactly.
Then you've got the low fidelity data, think simulations, simplified models. It's much easier to come by, but it might not capture all the nuances of the real deal.
Right.
Train your car only in a super basic sim, and it's going to be clueless when it encounters a real world traffic jam, right?
Totally. You'll get some skills transferring over for sure, but it won't be the full picture.
So this paper is all about trying to solve this this kind of fundamental tension, right? How do we leverage both types of data, the good but scarce, and the plentiful but imperfect?
Yeah, the authors here introduce this really cool framework they call Multi-Fidelity Policy Gradients, or MFPG for short. It's all about making the most of that precious high-fidelity data by combining it with a larger amount of the cheaper, lower-fidelity stuff.
It's kind of like having a coach who can give you really targeted feedback based on your performance in a few high-pressure games, but then also has you practicing drills and scrimmages to really solidify those skills, right?
Yeah, great analogy. You're getting the best of both worlds. And the results they show in the paper are pretty remarkable. You see some really substantial improvements in learning speed and overall performance compared to methods that just use one type of data.
So before we get too deep in the weeds, I think it'd be helpful to step back and maybe just remind ourselves about like the basics of policy gradient methods, right? These are the core algorithms at play here.
Sure, yeah. So in RL, you've got an agent interacting with an environment. The agent takes actions, the environment changes, the agent gets rewards. The goal is to find a policy, basically, a set of rules that tells the agent what action to take in any given situation that maximizes those rewards over time.
Okay, so the policy is like the agent strategy, right?
Exactly. And policy gradient methods are a family of algorithms that learn these policies by directly estimating how to change the policy that's the gradient in order to increase the expected reward.
Okay, and I remember one of the big challenges is that these gradient estimates can be really noisy, especially when you don't have a ton of data.
Absolutely. And that's where the whole idea of control variates comes in. They're a common technique for reducing variance in statistical estimation.
It sounds like this is going to be a key piece of the MFPG puzzle.
Oh, it's totally essential. It's the bridge between the high fidelity and low fidelity worlds. So let's dig into the nitty-gritty of how the authors formally define this multi-fidelity setting.
Right, lead the way.
So they use the framework of Markov decision processes, or MDPs. This is basically a way to mathematically describe the environment and how the agent interacts with it. You've got states, which capture the current situation, actions the agent can take, transition probabilities, which describe how the state changes based on the actions, and rewards associated with certain state action pairs. They define the high-fidelity environment, call it MH, as an MDP.
So that's the real deal, right? Or the most accurate simulation we have.
Yep. And then they define one or more low-fidelity MDPs, call them MLO, which might have different dynamics, different rewards, but crucially, it's much cheaper to get data from them.
Okay, so now we've got these two different MDPs. The high-fidelity one we ultimately care about, and the lower-fidelity ones we can use to gather more data. But how do we connect them? How do we ensure that what we learned in the simpler, cheaper MDP actually helps us do better in the more complex, expensive one?
So the authors really stress this idea of correlation. That's the secret sauce. You want to make sure that the data you collect in the low-fidelity MDP is somehow correlated with the data you'd collect in the high-fidelity MDP. If the two environments are completely unrelated, then the low-fidelity data is just going to be noise, right? It won't help.
So how do they make sure they're correlated?
They do this really clever thing with trajectory sampling. Imagine you're running two simulations side by side, one in the high-fidelity environment and one in the low-fidelity environment. You start them both from the same initial state. Then, instead of letting the agent choose actions independently in each environment, you use the same sequence of random numbers to guide those action choices.
So the agent might end up taking slightly different actions in each environment because the dynamics are different, but the underlying intention behind the actions is the same.
Exactly. The transition dynamics and reward outcomes might diverge as the simulations play out, but the initial intent, driven by that shared random seed, creates a correlation between the trajectories. This is how they tie the two environments together, even if the details of what happens along the way are different. They even have a specific algorithm, algorithm 1, that outlines this whole process.
Okay, so now we've got this method for generating correlated data from both environments. How do they actually use this data to improve the policy?
All right, so remember, the goal of policy gradient methods is to estimate how to adjust the policy, the agent's strategy to get higher rewards. The way they do this in MFPG is by constructing a new, more stable estimator for the policy gradient.
More stable.
Meaning less noisy. Remember, the high-fidelity data is limited, so the gradient estimates from that data alone are going to be pretty jittery. So they combine the standard high-fidelity gradient estimate, which we can call x by theta tau, with a control variate derived from the low-fidelity data. This control variate, let's call it x by theta tau, helps to smooth out those fluctuations in the high-fidelity gradient.
So it's almost like using the low-fidelity data to filter out some of the noise in the high-fidelity signal.
Yeah, that's a good way to think about it. And because we have so much more low-fidelity data, we can get a much better estimate of this control variate, which in turn helps us get a more accurate and less noisy estimate of the overall policy gradient.
This is making a lot of sense now, and they actually provide the formula for this new combined estimator, right?
Yep, they call it z pi theta. It's a combination of the high-fidelity gradient, the low-fidelity control variate, and a couple of scaling factors, one of which, C, is chosen to minimize the variance of this whole thing. The cool thing is, even though we're incorporating this extra information from the low-fidelity environment, the estimator remains unbiased.
Unbiased meaning?
On average, it still points in the right direction. We're not introducing any systematic errors by using the low-fidelity data.
Nice. And they show how to plug this new estimator into both REINFORCE and PPO, right?
Exactly. Those are two of the most popular policy gradient algorithms. So they develop MFPG versions of both, and they show that by using this multi-fidelity approach, they can get much faster learning and better overall performance, especially when the high-fidelity data is scarce.
All right, so let's talk about the experiments. What kind of environments did they use to put this to the test?
They used a bunch of classic control tasks from libraries like Gymnasium and Mujako, things like cart pull, inverted pendulum, some more complicated ones involving simulated robots like Swimmer, Walker 2, Topper, Half Cheetah, pretty standard benchmarks in the RL world.
And for the low-fidelity environments, how did they create those?
They used a few different tricks depending on the task. For some, like cart pull, they just simplified the physics, linearized the dynamics. For others, they tweaked things like the gravity or the reward function to make it easier for the agent to learn in the low-fidelity setting.
Okay, so a mix of methods to create a lower-fidelity version of each task.
Yeah.
And what were they trying to show with these experiments? What were their key claims?
They had 5 main claims they were trying to support. First, they wanted to show that their MFPG approach actually does reduce the variance in the policy gradient estimates. They compared it to regular single-fidelity methods with and without using other variance reduction techniques like value baselines or larger batch sizes. And across the board, they found that MFPG consistently led to much lower variance. They even have a nice figure in the paper figure 3 that shows this really clearly.
So point-proven MFPG does a better job of dealing with the noise in the high-fidelity data. What about their second claim?
That one focused on what happens when you're really starved for high-fidelity data. They specifically looked at scenarios with a very limited batch size, just 100 samples per update. And they found that in these data-scarce situations, MFPG completely blew the single-fidelity methods out of the water. They got much higher rewards, like 2 to 4 times better in some cases, and the learning curves were much smoother.
That's a pretty compelling argument for using this approach when data is really a bottleneck. What about when you have more high-fidelity data?
Yeah, their third claim addressed that. They gave the baseline methods a huge advantage, like 10 to 20 times more high-fidelity data, and even then, MFPG was still competitive. In some cases, it still outperformed the single-fidelity methods, and in others, it was at least on par with them.
So even when the playing field is tilted towards the traditional methods, MFPG can still hold its own. That's impressive. What was their fourth claim?
This one was pretty interesting. They wanted to see how robust MFPG is to having low-fidelity environments that are very different from the high-fidelity one. So they cooked up this scenario where the reward in the low-fidelity environment was actually the opposite of the reward in the high-fidelity environment. You'd think that would completely mess things up, right?
Yeah, sounds counterintuitive.
But even in this weird situation, MFPG was still able to learn effectively. It highlights the power of that correlated trajectory sampling. Even if the reward signals are misaligned, as long as the actions the agent is taking are correlated, there's still useful information to be gleaned.
That's fascinating. All right, what about their final claim?
This one emphasized the importance of that reparameterization trick we talked about earlier. That's the technique they use to ensure that the actions are correlated, even if the states in the two environments start to diverge. They ran experiments with and without this trick, and the results were very clear. Without the reparameterization, the performance of MFPG dropped significantly. It really underscores how crucial that technique is for making this whole thing work.
So they've got the theory, they've got the experiments, and it all seems to hang together really nicely. Now let's zoom out a bit and think about the bigger picture. How does this work fit into the broader landscape of reinforcement learning research? What are some of the historical threads or trends that led up to this paper?
So the idea of using multiple fidelity levels has been around for a while in other fields. Like engineers use multi-fidelity models all the time when they're designing things. They might start with a really simple model to get a general sense of things and then gradually refine it as they get more information. And in RL, researchers have been battling the problem of variance in policy gradient estimates for a long time. They've come up with techniques like reward baselines and value functions, which are essentially forms of control variates.
Okay, so using multiple fidelities and using control variates are both ideas that have been floating around for a while.
Exactly. But what's really neat about MFPG is that it brings those two ideas together in a really elegant and effective way. It's not just about reducing variance within a single environment. It's about leveraging information across multiple environments with different fidelities. It's a new way of thinking about how to use data in RL.
And it sets it apart from other approaches like curriculum learning or sim-to-real transfer, right?
Yeah, those methods are more about the training schedule. Start with an easy environment and gradually ramp up the difficulty, or train in simulation and then fine-tune on real data. MFPG is different because it's directly integrating the multi-fidelity data into the policy gradient estimation itself. It's a more fundamental change to the learning algorithm.
So if you had to boil it down, what would you say are the most important and kind of surprising takeaways from this paper?
I think there are three main things. First, they've provided a really solid theoretical framework for combining multi-fidelity data in policy gradient methods. It's not just a hack, it's a principled approach that has clear mathematical underpinnings. Second, their correlated trajectory sampling method is super clever. It's not immediately obvious that you could connect these different environments in a way that would actually be beneficial for learning, but they figured out how to do it. And third, the empirical results are very convincing. They've shown that this approach can lead to really substantial improvements in both data efficiency and overall performance.
All right, now for the fun part, novel notions. What are some future research directions or extensions that this paper makes you think about?
Okay, here's one that I find really intriguing. Imagine you have access to not just one or two low-fidelity environments, but a whole bunch of them, like a whole spectrum of simulators with varying degrees of fidelity and cost.
So instead of just high fidelity and low fidelity, you've got a whole hierarchy of fidelities.
Exactly. And the challenge then becomes, how do you decide which simulators to use at each stage of the training process? You could imagine a more dynamic version of MFPG that learns how to allocate its data collection budget across these different simulators.
So instead of just picking one or two simulators beforehand and sticking with them, the algorithm could learn to adapt its strategy based on what it's learning.
Right. Initially, it might focus on the cheapest, lowest fidelity simulators to get a broad sense of the policy landscape. But as it gathers more experience and more high-fidelity data, it might start to realize that certain mid-fidelity simulators are actually more useful for certain parts of the task.
Because they happen to capture some specific aspect of the high-fidelity environment really well.
Exactly. So it could start to shift its resources towards those more informative simulators, even if they're a bit more expensive. It becomes a much more strategic and targeted use of the available simulation resources.
That's a really cool idea. You're basically meta-learning the best way to use the simulators.
Yeah, and I think there's a lot of potential there. It connects with work on adaptive experimental design and active learning. How can we learn how to learn most efficiently?
Okay, that's one novel notion. What's another one that comes to mind?
All right, here's another one that builds on the idea of uncertainty. So some low-fidelity models might not only give you cheaper data, but they might also be able to give you some estimate of how confident they are in their predictions. Like maybe you have an ensemble of low-fidelity models and you can look at how much they agree or disagree to get a sense of their uncertainty.
So it's not just about the data itself, but also about how much we should trust that data.
Right. And the idea is that we could incorporate these uncertainty estimates into the MFPG framework. So when a low-fidelity model is really uncertain about its prediction, we might want to downweight its contribution to the policy gradient. But if it's very confident, even if it's not perfectly accurate, we might want to give it more weight.
Because that confidence might indicate that it's capturing something important about the task, even if the details are a bit off.
Exactly. It's like if your friend who's not a great cook tells you a recipe is amazing, you might take it with a grain of salt. But if your friend who's an amazing chef tells you a recipe is just okay, you might still try it because you trust their judgment.
Yeah, that makes sense. So we're basically using the uncertainty estimates to filter the low-fidelity data even further.
Right. And I think this could make the whole approach even more robust and reliable, especially when dealing with low-fidelity models that are very different from the real environment.
It's like a way to mitigate some of the inherent biases in the low-fidelity data.
Yeah, and it connects with a lot of interesting work on uncertainty quantification in machine learning. How can we use uncertainty estimates to make better decisions, both in terms of how we collect data and how we use that data to learn?
These are some really cool ideas. It really shows how much potential there is for building on this work. And as always, we want to remind our listeners that these are just speculative ideas for future research.
Of course, just food for thought.
All right, so as we wrap up this deep dive, what's the big takeaway message you want our listeners to remember about MFPG?
I think the main message is that this is a really promising approach for making reinforcement learning more practical for a wider range of real-world applications. By cleverly combining data from different sources, it offers a way to drastically reduce the amount of high-fidelity data we need, which is often a major bottleneck.
It's like a turbocharger for RL, especially when data is scarce.
Exactly. And I think this is just the beginning. There are so many interesting directions for future research, and I'm really excited to see where this line of work goes.
For our listeners who want to dive deeper, we'll be sure to include a link to the paper in the show notes. And here's a final thought to ponder as you go about your day. As we get better and better at creating these incredibly rich and detailed simulated worlds, how will techniques like MFPG change the way we train and interact with AI? Will it blur the lines between simulation and reality even further? Thanks for joining us for this deep dive.